Now go back to unit 5 again. Unit 5, in this case 5-1, in this case. So I'm going to provide you a quick review. 5-1 is really about the nth roots and radical and what they call the rational exponent. Now, rational exponent, why do they use the term rational? In mathematics, every time you hear people say rational, you have to translate it into something different. Rational is not like psychology, talking about rational being logical. In math, they say rational, what do you think that means? Anybody can tell me what rational means? Ratio. Huh? It's a ratio, that's right, fraction. A over B. So when they say rational exponent, that means the exponent will have like a fraction. Does that make sense? So the exponent is a fraction, that's called rational exponent. Alright, so in this case, the example here, and this is a review, so I'm not going to spend too much time. I'm going to assume that you already done the work. And you had done the work with Mr. Chen. So for example, we want to say rewrite fifth root of 32 to the 4th power. Okay, well, so in this case, this is a nth root, so the expression. Right? It notates a value, right? Some sort of value. And so I can rewrite this, right? I can rewrite this into 32 to the 4th power and to the 1/5 power. And I can simplify this a little bit more. So I can simplify this into 32. And how we do this is based on the 5 properties. I think you all receive. Have you ever seen this one? Yeah, you know what I'm talking about, right? You know what I'm talking about? So over here, the top, the very first section says the 5 properties. You know you need to memorize that? Right? You need to memorize that? 5 properties. So one of the properties gets expressed here is you have exponent of exponent, then you multiply, right? So it's 4 times 1/5, so 4/5. So in this case, right? So in this case, you have an exponent that is in fraction. In fraction, in mathematics, we term that rational. So this is a rational exponent. Right? So this is a rational exponent. This has a term with a rational exponent. So this is, and this one is just a valid process of, and the idea here is not so much, but the point here is this, is that, and you'll notice that this, even though over here there's a call to action telling you to rewrite something, but even if I don't do this, if I erase this, you have to be able to navigate from this place to this place. It's a fluid, dynamic process. Sometimes on a test, you'll be given like this and say, hey, rewrite this into radical. Then you go this direction. Does that make sense? And sometimes you be given this, write it into a rational expression. You say, oh, okay, then I go this direction. You have to be able to comfortably navigate between the two. Get it? Question? No question. All right. We're going to move on from 5-1 to 5-2 now. 5-2, I'll start with this example, and I'm going to ask you to solve this. Rewrite 81 to the 5/6 power times 81 to the negative 1/3 power. Go ahead. Start working on that. And in about exactly 60 seconds, I'm going to come around and see how you're doing. work out the process. The call to action could be rewrite or simplify, or there's different ways to say it, but it really is the same kind of problem. Okay, you just have to be able to know what they're asking. Write out the process. Don't miss any steps. Every step represents a part of your thinking.
So here we got an issue here. So the idea of that is to come with some. So we walk around, then the truck, and in that whole we do the same thing. So rather than just come with something, walk with it, so you want to go back to the property right here, right? So what you did is you got,
Oh, I'm sorry. I think I confused some of you. This should be 81 as well. I'm sorry. That was my bad.
now you get it. This is a one drawing. I'll check you. Alright, so okay, well I'll give you 60 more seconds then. Alright, see if I can see a different result. Alright. Let's see if we have more winners this time.
No, I was really confused. He was looking at the other questions and I thought
Good. All right, now let's come back here again. Couple observations. Number one. Some of you quickly turn this back into radical and work with the radical. So I saw some people doing, say, 6 roots of 81 to the 5th power and so on, and whatnot. The whole point about this chapter is that radical and roots are so cumbersome to work with. If we can we can avoid it, we'll avoid it at all costs. So turn that into exponents, right? And so we see this and we don't like it, so we turn it into exponents. Exponent expressions are much easier to work with. So that's number one. Number two is that you got you remember I reminded you there are 5 exponential properties that we work with? Because we're working with exponents now, then follow those properties. One of the properties that we have was a to the m power times a to the n power. Notice exponents are different, bases are the same, and they multiply each other. And here's what I noticed is interesting. Some of you did this. You decided that you're going to do it this way. A times A, and then the exponent. Now that's not true, right? It is simply the base, the same base, and then m plus n. So you can do that. So this is what we will do. We will say, okay, if this is the case, then it's just really one exponent, one base, to the 5/6 power plus negative 1/3 power. Right? Because this is a to the n, this is a to the m times a to the n. Right? And it's a to the m plus n. Now, the logic of this property, we actually talked about it previous time when you were with me. So I actually showed you that this is true, this is valid, right? So that's where we end up. Now, so then that's just a matter of dealing with the exponent, and we know how to deal with addition or subtraction of exponent, right? And this is 81 to the 5/6 minus 2/6. So we end up with, that's right. So 81 to the 3/6 power And if it's 81 to the 3/6 power, it is what? 81 to the 1/2 power. But we also know that 81 is 9 squared. So 9 squared to the 1/2 is 9 to the 1. So it's just 9. Now, if typically, right, in my logic, notice I took a different direction than what some of you may be taking. I say 81 to the 1/2 power is 9 squared, right? 9 squared to the 1/2 power. So 9 squared to the 1/2 power is 9 to the 2/2, which is 9 to the 1 power, which is 9. That's one way to think about it, right? But on the other hand, you can say 81 to the 1/2 power is square root of 81. Well, we all know square root of 81 is 9. Now, that's one way to think about it, but you say, well, it leads to the same answer. Yes, but your brain kind of going in two different directions, using two different properties, which is, you need to be able to do both. Does that make sense? Yeah.
I'm a little confused with the one half goes. Like, when you find the square root of 81.
Where? From here to here?
Yeah, when you find the square root of 81, it's just 9, so where does the 1/2?
Yeah, so there are two different directions, right? We can say this is square root of 81, and then by familiarity, you say, oh, square root of 81, 9 times 9 is 81, so square root of 81 is 9. Right, this is based on, that of course, this is easy because you get an easy number to work with. But you could also think of it this way, that 81 is 9 squared to the 1/2 power, yeah? And then one of the properties that we have, one of the major properties that we have was a to the m to the n power is a to the m times n, right? So this is m times n, so it becomes 9 to the 2 times 1/2, which is 9 to the 1, which is just 9. It's a little complicated because 81 is an easy number to work with, so you say, I don't want to work pretty good. Waste so much time to just go through that. It says something that you really want, right? And so you have to be able to flex your brain muscle to be able to go in different directions. These are just different tools, toolbox. That makes sense? You need to know all. All right. Give you another one. We write x, y, third power over x 1/2, the whole thing to the third power. All right, go. 60 seconds first, and I'll come around. This is fairly simplified expression. Okay? You have x and you have y and you have all the math in the numerator and denominator. How can you just get one x and one y? Okay, let's do this. I think I give you enough tips to kind of unstuck you a little bit. Let's go through this again, okay? Just kind of see this whole process, how we go through this process in one solution steps, right? Or one solution process. Here's interesting because some of you get a little confused. When these things are all like clustered together, you have to ask yourself, like, what does that really mean? It really means that when you have an x and a y with a different exponents, number one thing you have to think about is, even though it's not written and notated, it's actually multiplication, right? It's multiplication. It's not addition or subtraction, so you cannot like do some like weird stuff. Okay? So that's number one point, because I saw some of you make some mistakes as if this is a plus sign. So that means that your denominator is the only denominator for this whole expression, not a denominator for the x and a denominator for the y's cube. Okay, because that's number one common. Number two common is, well, let's just go ahead. We have an exponent out here, and this exponent will distribute because it's an expression that has some exponent. Okay, I remember. I noticed some people have made some mistakes. When you see x here and x here, and I saw some people just pass it out. Like, some of you just did this. So, whoa, wait a minute, you can't do that. There's a force shield around it. You see what I'm saying? This x is protected by the exponent of 1, and this x is protected by the exponent of 1/2. Don't mess with it. You can't mess with it. You can't just like cancel. Go on Joyride and cancel things out. No, you can't. Alright, so now the only thing you do the next part is deal with this exponent that is outside of the whole thing. So then you distribute this into here, and into here. When I say distribute means multiply the exponent. Okay, so then you end up with a x1 times 2/3, y2 times 2/3, and over here x1/2 times 2/3. Okay, don't mind the details. Sort through them, and pay careful attention to kind of walk through and untie the thread. So in this case, right, the top, x to the 2/3, and then y squared, right? Y squared. Makes sense, right? Y squared. And then on the bottom, you got x to the 1/3. You can write it this way, but if it helps you to visualize this, and I'm going to erase this and write the same thing again, except I'll position it a little bit differently. I'll put it right here. X to the 1/3. That means I need to simplify this portion, yeah? This one is done deal. I got that part done. I got y squared. I just need to take care of the x. So in this case, remember the property? A to the m over a to the n. We have the bases are the same, the exponents, and then dividing in a fraction is a to the m minus a, right? So that means this part is x to the 2/3 minus 1/3, and y, bring it down, y squared, don't mess with it. Don't mess with it. And then 2/3 minus 1/3 is 1/3, so it's x to the 1/3 y squared. If you and so this will be perfectly legit expression at the end. But if your test problem says, hey, rewrite this back into radical form. Rewrite this back to radical form, what would you do? I keep y squared first. X to the 1/3 will be cube root x. This will be in the radical form. I didn't ask you to do that, so you don't have to do that. If you come up right here, it's totally fine. But if the problem asks you to do a radical form, then you do that. Got it? I do want to go over, because of time crunch, I'm going to give you additional problem, and then I'll come back with another variation of this type of problem. All right, I want to give you this problem to solve, which is, this comes out a lot. They say, for example, 2/3 plus square root of 5. And they ask you to simplify, or rewrite, or simplify. It's different verb form to tell you what that you need to basically make this look a little nicer. The reason why it doesn't look nice is because, number one, it's radical. Radical is fun, radical. But it's a flexible radical. This radical is in the denominator. We don't like radical in the denominator. It's a real radical. We want to find every way we can to get rid of the radical in the denominator. But radical, this radical is a square root, right? So we saw a square root of 5. It would be nice if we had square root of 5 squared and turn that into 5, right? So I'm thinking, okay, how can I find a way? Is there a tool that I can make this expression where somehow at the bottom of the denominator it has to be squared? Squaring the 3 and squaring the 2 and the 5. I end up with no value. Now, of course, when I do anything like that, it changes the whole balance, right? So we have to like do something on the plot too. But any strategy that you have learned before doesn't apply to this. So number one, for expression, simplifying expression, you know that you can multiply anything that is equivalent of 1, right? And 1 can be anything over anything, right? 1 is equal to 5 over 5, 10 over 10, 1,000 over 1,000, or c squared over b squared, or whatever. If there's anything that you will multiply the top, you multiply something on the bottom, that's 1, and then you can manipulate the expression. What is it that we can do with this that can get rid of the radical on the bottom? Yeah. Multiply everything that I said. Oh, okay. So suggestion was, can you like square it? But if this thing inside that red parentheses is 4, 4 squared becomes 16, so you fundamentally inflated the value. Right? You're not simplifying. This is not equation, this is just literally a term, but you gotta like change the form. But changing the form should not change the value of the form. So we can't square it. If we square it, we fundamentally change this whole value, right? You can't do that. That's the reason. What? Okay. 5 to the 100, yeah. So don't write this yet. Okay. We don't know this. 5 to the 1/2. And what do you suppose that we do with that? We still have to do something to it, right? All right, here's a trick. This is a trick that happens all the time. I don't know. I guess SAT doesn't. School doesn't take SAT anymore. But if you fancy still taking SAT, this is a very valid strategy. This is what you do. I had to go back to what you learned before. What you learned in the polynomial, you remember the binomial expansion. This is in a bunch of binomial expansion we learned some strategies. This is where it's important, and you have to memorize it, right? You got a plus b squared equal to a squared plus 2ab plus b squared, a minus b squared, a squared minus 2ab plus b squared. And there's another one. There's one here that says a plus b times a minus b is equal to a squared minus b squared. Do you remember that? Do you remember you learned something like that before? Yeah? The consequence of FOIL, right? Doing FOIL. Which one? Out of these three. And I give you pretty limited choices. I can write out a bunch of binomial extensions, but I give you just three, just to start. Just to make things a little more interesting. Which of the three would you guess, or educate guess, that will get you, that we can use to for the benefit of this problem? Which one? The top one? Well, the top one, if we square the bottom, we'll get this thing that gets more complicated, isn't it? Okay, and then you say the third one. Okay, how? So now, and he's actually right. This is the third one. So the question is, how do we do it? How do we apply this third one for the advantage of this thing? Right now, you have 3 plus square root of 5 in the denominator. That is our headache. And you got the square root of 5. That is the center of the headache. And if I can somehow find a way to square the square root of 5, square root of 5 becomes 5. I gotta get something squared. But notice, this is something plus something. So something plus something. So if I can multiply the same thing minus that same thing, I end up with that first expression squared minus the second expression squared. Right? You notice that? If this is A, if this is what we call A, and this is what we call B, A plus B, then I can multiply A minus B, and I end up with A squared minus B squared. Take a look at this. I'll use a different color. Maybe that will help. All right, so first of all, you have to have parentheses, right? Because if you lose parentheses, you may get confused. Because you're applying this property, so I'll go ahead and put a parenthesis around this. All right? So I'm going to go ahead and on the bottom, be bold, 3 minus square root of 5. Right? Because A is 3, B is square root of 5. Right? So somehow equal sign is over here. Equal sign is over here. Now, I cannot just take the expression and multiply by something on the bottom and think that that's a good idea because I like it. We have to follow mathematical logic, and we can't inflate or deflate the value of that expression. So if you multiply the denominator by 3 minus square root of 5, what do you do in the numerator? That's right, you multiply the same thing. So you gotta extend this fraction, and then you multiply 3 minus square root of 5. Okay? So guess what happened? Right? Guess what happened? The bottom becomes what? Becomes 3 squared now, right? A is 3, A squared minus B squared, so A is 3, so it's 3 squared. Minus B is square root of 5, but that will get squared, so square root of 5 is squared. On the top, this is just 2 times this binomial, right? So it's 2 times 3 is 6, minus 2 times square root of 5, 2 square root of 5. Okay, so now we can go ahead and the top, I can't do anything with the top, so I'll keep the top as it is, 6 minus 2 square root of 5. On the bottom, 3 squared is 9, minus square root of 5 squared is 5. Look at that. So on the bottom, 9 minus 5 is 4. Top portion is 6 minus 2 square root of 5. Ah, I'm almost there. This is looking pretty nice. No radical in the denominator. I didn't do anything to inflate the expression or deflate the expression. I utilized one of the tools in binomial, and I borrowed this one before and put it over here. And all I need is simplify this. They are all factor of 2, right? 6, 2, and 4. And again, 6 is square root, 2 square root of 5 is separated by a minus, not multiplication. Before this is multiplication, we treat them as a whole. This one actually has 2 terms because it's separated by minus. So you have to make sure that you have these 3 elements have common factors. And common factors will be 2. So your final answer, 3 minus square root of 5 over 2. Right? Questions? Before I give you another one to work on. Right, so you gotta work on this one. So I go. Okay. A notch. More complicated. Notch. And even though you have a radical on the numerator, that's not really a big problem, right? We're okay with radical on the numerator. What we don't like is a radical in the denominator. Address that first. So we have here, treat this as A, treat this as B, A plus B. So you need to multiply A minus B. If you do that, you do it up and down, and then simplify. The radical but you want to make sure that that radical is squared out. You can't square it just because you say so. You got to follow the problem. So over here we have A plus B, 2 things that added together. If we multiply by something that subtract the same two things subtract each other, you end up with that same thing squared minus that same the other thing squared. Okay? So right now there's a 3 plus square root of 5. You multiply by 3 minus square root of 5, you end up with 3 squared minus square root of 5 squared.
Oh, I'm gonna equal to 1, we multiply by 1.
That's right. Use the same process. Oh, I'll let you know. Okay, let's take a look at this. All right, ready? So here, if you look at the previous problem, that's why I keep going back to the previous problem, because if you follow the previous problem, this should not be a too difficult issue. Previous problem, this was the original form, right? This was the original form. And our problem was in the denominator. So then we take the denominator, we look at this in a similar I, with a similar I as A and B. So this is A and B. So then and since this is plus, so we multiply by the same two terms but minus, right? And because we can utilize this. So in this case, we'll also zero in on this thing right here. We're not going to worry about the top, we're just going to worry about the bottom. And this is A and this is B, right? This is A and this is B, and this is A minus B. So I can do an A again plus B by doing it over here, right? 3 plus square root of 3. Now, if I do that on the bottom, I need to do that on the top too, right? So I'll have 3 plus square root of 3. I'll make sure I put this in all of that, just so that I can keep track of them. Okay, so that's really the strategy. The reason why is because A minus B times A plus B becomes A squared minus B squared, right? So on the bottom, A squared is 3 squared minus B squared. B is square root of 3 squared. Okay, so I don't want to rush to try to finish this. I just want to make sure I clean up the top. The top, right, you do the formula, right? 2 times 3 is 6, right? 2 times positive square root of 3 is positive 2 square root of 3. And then negative square root of 5 times 3 is negative 3 square root of 5. Negative 3 square root of 5. And lastly, negative square root of 5 times positive square root of 3, right, is negative square root of 15. Okay. So then on the bottom, 3 squared is 9. Square root of 3 squared is 3, which is 9 minus 3, which is 6. And on the top, 6 plus 2 square root of 3 minus 3 square root of 5 minus square root of 15. Ask myself, is there any more to simplify? Probably not. That's the answer. Good? Question? Which one? You got it? Okay, so I want to leave you one thought here, which is going to be on the next portion, which is 5-3, which is radical functions. This is graphing. And when you do study ahead, next time when we meet, I'm going to give you lots of these. The question is, how do you graph alphabetic space square root of x, right? And just to unveil the mystery, it's very simple. It looks like this. Starts right here and boom, like this. Now it doesn't plateau. It doesn't go eventually. There's no asymptote. It will just keep going higher and higher and higher and higher and higher and higher. That makes sense, right? If x is equal to 0, square root of 0 is 0, right? So it starts right here. Square root of 4 will be 2. So if you got 4 right here, this will be 2. If you got, say, 9 over here, it will be 3. It makes sense, right? So basic function, the form, it's like every time you have a square root function, whoop, goes like this. Now you say, well, what happened to the negative? Well, can you have a square root of negative? Can you have a square root of negative 5 or 4? Square root of negative 4. That's why the whole thing is missing on this side. Now the question right now for this kind of problem is, when I ask you to familiarize yourself with this kind of function, is to say, well, what happens if I had square root of x plus 1? Or what if I had 2 plus square root of x? What if I had 3 times square root of x? And what kind of function, what are those things going to shift this function, the basic foundational function, around the graph? That's the key question that we're going to talk about next. Got it? Have a good day.